Recording in progress.
Sorry about that. Okay, so the next couple of weeks, in my opinion, there's some of the harder material in the course. So the next few weeks we're going to be doing, we just did rotational stuff, and we'll see a little bit more of that in the next couple of weeks. We're going to do momentum today, and then as a true grab bag of topics, this next section leading up to midterm 2 also has a little bit of thermodynamics on it. So it really is a bunch of different topics. I think it's kind of the nature of courses like these is that they're trying to cover, you know, all of physics in a half semester or something. So we're going to be jumping around a bit. I think that rotation is pretty hard. And I think part of it is because, as we'll see today, a lot of ideas related to both linear and rotational momentum really involve thinking about things in terms of vectors, which adds an extra sort of dimension of things to keep track of in the problems that you're solving. Okay, so today we're going to talk about linear momentum. And I mentioned linear to draw a contrast with angular momentum, which we've seen before and which we'll see again in a couple of weeks. So we're going to talk about linear momentum, and then we're going to talk about collision problems, which is the textbook classic kind of problem you find in a physics course that involves having to keep track of momentum. Okay. So momentum is defined using the formula, the vector p, we always use p to note momentum in physics. The vector p is equal to m, the mass, the scalar, times v, another vector, where v is going to be the velocity. So let's go ahead and fill that in. So this is momentum. This is mass. And this is just velocity as we've always seen it. Okay, so momentum, one thing that we can see right off the bat is that whatever direction your velocity points in, your momentum points at, right? Because all that I have here is a scalar mass. Mass doesn't affect the direction you point, it's just some number. So basically all the momentum does is it takes your velocity vector and it stretches it by however big or small your mass is. So if we check the units, right, we know that offhand velocity has units of meters per second. Mass has units of kilograms, all in SI. So momentum doesn't have any particularly elegant units. Momentum is just going to have units of kilogram meters per second. So, you know, this is obviously a very derived unit, but when you're checking things and checking formulas, it's useful to know what this should have the units of. Okay, so momentum is useful because this is going to basically measure the tendency of an object to continue moving along the trajectory it was already on. So to give an example of that, if I have, you know, an object that, if I have like a bicyclist, like one of these really fast bicyclists on Speedway, and they move at, this is my bicycle, it looks weird. And they're moving at, I don't know, let's say, I think 15 meters per second would be pretty good for a bicyclist. I could be wrong. But they have a mass of, I don't know, I think, let's say 100 kilograms. So maybe they're a big bicyclist. Okay, so they have a certain value of momentum. But then if I have something like, there's these trucks, I don't actually know what they carry, but they seem to go up and down Speedway all day. They have some access. And, you know, there's a little man driving the truck. And that's also going 15 meters per second because they're stuck behind the bicyclist. That might have a mass that's more like 1,000 kilograms. It's a huge, heavy car. I don't know what they keep in it, gold bars or something. Okay, so intuitively, these two objects have the exact same velocity, right? They're all moving at a velocity of 15 meters per second, and I'll say that they're moving in the x-hat direction. So I'll just define my standard coordinate axes. So in principle, they're moving at the same velocity, but intuitively, if I want to stop a bicyclist, right, all I'd have to do is, you know, like stop them, or maybe I'd need a friend's help or something. But if I want to stop the truck, you know, good luck with that. And so even though those two things are moving at the same velocity, intuitively, the big one that has more mass, that's going to be the one that has more momentum that should be harder to stop. And this captures this idea that momentum, unlike velocity, momentum really gets into this idea that if you have a lot of mass, once you get started moving, you tend to sort of keep moving. It's harder to change the direction or the speed that you're going. So momentum is the tendency to continue your current motion. Okay. So momentum then is going to come in handy when we have problems that involve velocity changing, especially abruptly. So the typical kinds of problems you'll see momentum in are going to be stopping problems So you have a lot of genre of problems where you say, a truck suddenly abruptly stops. How quickly does it take to stop or something like that? And then the really classic example of this are collision problems. So this is an entire genre of problems you'll find on the MCAT and in textbooks. And it has something of the form of, ball one hits ball two. What is the final velocity of the two balls? They all have some form like that. Sometimes they don't say balls, they say cars or something. But whenever you see something that refers to something colliding or hitting something else or recoiling or something like that, that's usually a clue that you have something involving momentum involved. And so this is why we introduced this concept, which at least in principle seems very similar to stuff we've seen before, but it turns out that this specific quantity is useful to keep track of for collision type problems. Okay, and the reason for that is going to be, and we'll see this downstream a little bit, is that in the absence of external forces, momentum is conserved. Okay, so we've seen energy conservation loosely before. We haven't done, I don't think we've done any calculations with it yet, but I think we will in a little bit. So momentum is a vector that is actually conserved external to a system. So a lot of the problems that we might encounter that involve, maybe I have like my bicyclist, something like that, sure. And maybe I have them colliding with, I don't know, I don't want to do another bicyclist because that seems kind of mean. Maybe an empty bike on a bike rack or something. In principle, as that bicyclist collides or something, the total momentum of that individual changes, right? Because for example, if they're 100 kilograms and they go from V equals, 100 to V equals 0, in principle, their velocity changes, so their momentum should change because their mass stay the same. But the idea with momentum is that if I think of the entire system as one object, the total momentum across whole system is conserved. So what does that mean? So if my bicyclist hits something and stops, that means that the thing that they hit has to start moving. And this is why this comes up in recoil and collision problems, because what is a collision? It's me hitting something with something else, and then that causes that thing to scatter off somewhere. Or equivalently, if I have two things that sort of like hit each other, they either sort of stop because they cancel each other out, or they might bounce out, but their overall sort of the sum of their two momenta ends up being the same. And so this is going to end up being a pretty fundamental physical thing. We'll do some example calculations downstream of here in a little bit. But the idea is that the reason we care about this kind of esoteric quantity is because if you don't have external forces on your system, momentum is conserved. And we'll see one or two examples of that in a bit. Okay. So without forces, momentum is conserved. But in order to get momentum in the first place, you do need a force to gain it. So first we'll talk about how do I gain momentum? And the answer to that is that we're going to define a quantity called the impulse, which is going to basically be a measure of the change in momentum over time. Okay, so the impulse equals just a change in momentum. It's just a rebranding of the same formula. So if I have an object that starts out having some initial momentum, so maybe that was before it hit something or something, and then sometimes later it goes to having some final momentum. The impulse is traditionally just defined as PF minus P naught. So I'm going to write that down what these are. So this is the impulse. And this is initial, or that's, sorry, that's final. Final, initial. Okay, so the impulse is just another thing that has the same units as momentum. So if momentum was mass times velocity, so this should just have units of kilogram meters per second. But specifically, we use impulse when we talk about cases where something is changing due to something acting on my system. So the way that the impulse is derived is that we actually think about it as a quantity related to Newton's second law. Yeah, Newton's second law. So remember that when we introduced Newton's second law, right? Like most of us just sort of memorize, oh, F equals ma. Don't worry about it. But you'll remember that technically this wasn't quite right because you could have cases where your mass is changing. And so technically the proper form of Newton's second law is F equals d dt of p, where p was the momentum. And we sort of grazed by this concept quickly because we weren't using momentum then. But this ends up being pretty important here, is that force technically is any time derivative of momentum over time, or any change in momentum over time. And just to see where you might get this, so if P equals mass times velocity, if I take the derivative of P equals d dt of m times v, I'll get d dt of P. And then I need to actually use the product rule for derivatives. So that's d dt of m v plus m d dt of v. So I've just taken this derivative of a product and written as a sum. And then if I have constant mass, d dt of m equals 0, so then I can just cross out that term. Then I get P equals, I'm going to bring this down because the other term went to 0. M d dt of v, and the derivative over time of the velocity is just the acceleration. I forgot my d dt equals mass times acceleration, which is exactly what we saw before. So this is all consistent with what we saw of Newton's second law before, but we're going to use a slightly more general definition here that captures the idea that anytime I have a change in momentum, it's because a force acted on my system overall. Okay. So using this formula, we can derive what the impulse corresponds to. So if the impulse is a change in momentum over time, then we can define that using Newton's second law. So I'm going to write that F, the force in Newton's, equals the d dt of the d dt of P. So if I want, I can go ahead and solve this out. So I can say that I'm going to move this dt over there. And then I'm going to just keep the d and the p on that side. So I'm going to write that as F vector dt equals dp. So all I've done is just move the bottom part over there. Then I can integrate it just like I normally integrate problems like these, where I can say, what is the integral from initial time to final time? And that should equal the integral of this from initial momentum to final momentum. And I always use definite integrals, because if you have definite integrals, you don't get an integration constant. So you don't get a plus c when you do these integrals because they're definite. If they have known bounds, you don't get that. Okay, so I can go ahead and write that out. And I could say that this is equal to, if I simplify this and I go ahead and I say that F equals a constant, then I can simplify this a little bit more, and I can write this as, I'm going to move this down. I can write this as F T naught to TF dt equals the integral P naught to PF dp. So all I've done here is that F is a constant. It doesn't depend on time by definition. So that allows me to pull it out of the integral because it's just multiplying an integral by a constant. So then I could just write that F TF minus T naught, right? This is just me solving this integral. The integral of 1 is T. So then I just solve it from here to here. Equals PF minus P naught, where this equals the integral of that, just using the integral of 1 again. Okay, so then I can clean that up a little bit, and I can write that the force times the change in time equals the change in momentum. And we're going to define that change in momentum, or equivalently, this constant force over time as J, where this is the impulse. Okay, so the impulse has units of force times time, but it really just corresponds to a change in momentum. So they're all equivalent with each other. They're just different ways of describing the same thing, which is I had some MV, I have some different MV. How much did that vector change? Okay, and I'll just flag this, that this is under the assumption that f is a constant. And because I use that in order to get this f outside the integral, allowing me to solve that. Okay, so this is a useful formula to have because this is going to come in handy for cases where we have problems where you inject or add momentum to a system. So before we do that, let's just check that this is dimensionally consistent. So I'm going to go ahead and check the units of F delta T. So I know that force has units of kilograms times meters per second squared. You can get that from F equals ma if you want. This is technically a definition of a Newton in derived units. So that's going to be that first term. Then I have seconds, so I get kilograms over meters per second, which you'll recall is the exact definition of the units of momentum. So it looks like this F delta T does indeed have the same units as momentum. So this all seems to make sense. Okay, so what does that tell us? It says that if I apply a force over delta T, I get a momentum change. And intuitively, this makes sense because we saw before that when you had objects that were moving at a constant velocity, you had to apply force to get them to do anything differently. But this is really framing it in terms of momentum because this is the proper form of Newton's second law, is F equals dp dt. Okay, so just to get an idea of what this looks like in practice, let's use impulse to calculate a really sort of simplified example of what happens when you kick a soccer ball. And the book actually has they have a whole kind of essay about kicking a ball. They really get into it, but we're going to simplify that a little bit to just get at the sort of key idea here. Okay, so I'm going to write soccer. So in soccer, let's say I have a ball that's currently in play. So that ball is moving at some v naught. So it has some velocity. And maybe we're going to say that I'm currently staring sort of down at the ball from above or something, just to make it a little bit easier to see where the vectors are. Okay, so my ball, it's currently rolling. It has some v naught. And then I come in with my green foot and I kick the ball. And I can think of my kicking the ball as applying some impulse to the ball. Okay, so let's say I'm an okay kicker. And I kick it with some impulse J. Okay, so what is the impulse J? So J is how hard I kick, which is a force, times how long I'm in contact, which is a time. Okay. So let's say that I can kick with some force. I don't know, my kick force is J equals F kick. And let's say that when I'm kicking the ball, I'm in contact for, I don't know, let's say a third of a second or something, so a really short amount of time. So we're going to say that that's just some delta T, where in soccer, this might be, let's say that's less than 1 second, because usually when I kick it, I lose my foot pretty quickly or something like that. Okay, so this gives me what I need to calculate a change in momentum because I know how hard I kicked it and I know the delta T, how long I kicked it for. And those are the two things you need to calculate an impulse, which is the product of those two things. Okay, so the question is, what is VF for the ball after I kick it? And for this, we're just going to use the bare bones definition up here that describes what impulse is in terms of change in momentum. Okay, so I'm going to write this out. So I'm going to write that J equals delta P. So the change in the ball's momentum, delta P is PF minus P naught. P naught. And J is going to here correspond to my kick. So if I say that I kicked this at some F kick, and I was in contact with the ball for delta t, I'm going to set that equal to PF minus P naught, where I'm just using, again, this formula. Okay. So I have F calc delta T, and then I actually know P naught for my ball. So I can write F kick delta T equals PF, which is what we'd like to find, minus P naught, which is going to actually just be the mass of the ball times V naught. So whatever its initial velocity was rolling at before we kicked it. So then if I want to solve it, I can write that PF equals F kick delta T, still keeping my vectors intact, plus M V naught. And then if I actually wanted to solve for velocity, I could, because mass didn't change. And so I could write my PF as equal to just the mass of the ball times VF. So I could write this if I wanted as VF equals 1 over the mass of the ball, F kick delta T plus M V naught. Okay, so what does this really tell me? So it tells me one thing what I expect, which is that presumably the bigger this is, so either the harder I kick it or the longer I'm in contact, the more I can hope to change the momentum of the ball. Okay, but conversely, as the momentum of my ball has some super, super large mass, so I don't know, maybe it's made of lead or bismuth or something, that's going to make it harder to change from this to this, because this term is going to get really big, which is going to dwarf out this term. So in other words, the fact that we have m now in this expression for the velocity, this is a little bit different than kinematics, because this is going to basically mean that I pay a penalty for trying to kick heavy objects versus light objects, which kind of matches our intuition. Likewise, if I can't kick any harder, if I can somehow kick it for longer, so maybe I stay in contact for longer, I can still gain momentum because I have my force being applied over a longer interval. So I can either increase the duration of contact for the collision problem, or I can just increase the kicking at force itself. And both of those will change the momentum more than if I didn't do them. Okay. So this captures this idea that, the ball has some fixed mass, it has some velocity that wants to move along. I need to apply some impulse, which is a force over a time, in order to make an appreciable change to the ball. Okay, so one of the issues with momentum is that all of these things in this expression are vectors. And so you do have cases where you need to think about vector addition when calculating your final momentum or your final velocity or some combination thereof. So for example, if I'm a kicker and I have a ball that's moving, let's say that initially moves down, if I apply my kick, which I'm just going to write as J, which is just again force times delta T, if I apply my impulse perpendicular, right, I'm going to expect that to do something like, that's not a good arrow. There we go. If I apply my impulse perpendicular to my initial velocity, then I really expect that I'm going to get my VF to be going somewhere that way, where how tilted it is going to depend on the initial momentum and how hard I kicked for how long. Okay, so that means that I have a case where this can point one way, this can point another way, and this can point some completely different way. And that again is because this is vector addition we're doing here. So if this points along X hat, that points along Y hat, this will be somewhere intermediate. That depends on how big these different numbers are. Likewise, I can have cases where I maybe accidentally kick it a bad way. So maybe I have the ball that's going downwards, and then I kick it this way. So in that case, depending on how hard I kick it, I could get a case where, my ball is just going to move at some smaller velocity because I've kicked it against the direction it was heading. And that will manifest as when I do a calculation like this, I'll get a minus sign somewhere. So I'll basically have a kick that, even though I kicked it as hard as I could and for as long as possible, so my impulse was really big, I kind of undid the direction it was going already. So momentum captures not just this idea that heavy objects tend to keep doing what they're doing, but they also want to keep going in the direction that they're going unless I apply a force to them, which is very consistent with Newton's second law, but it really captures how mass couples into the problem. Okay. So one of the ways you'll see momentum popping up is using momentum to calculate forces, especially during really abrupt events like kicks, collisions, crashes. There's a whole genre of problem that you might find momentum in. So let's find the force average during a crash test. Okay, so I haven't seen the latest videos on how these are done, but I'm gonna imagine that a crash test looks something like this. So I have my car. It's not the nicest car. That tends to move at some velocity v naught. So I don't know. I think they usually push it rather than actually having gas in the car when they do these tests. So I have a car that's moving at some fixed velocity, and then in the factory they'll set up some giant wall or something, and then at some time later, this system will crash into the car, and so you'll get something that looks more like that, where now I should have VF equals 0. So this is a very toy demonstration of what a crash test might look like. So this is a classic kind of momentum problem because this is an example of a problem where the force actually will act over a very, very short interval of time. So the car is going to spend all this time making it to the wall, but when it actually crashes into the wall, that actual impact is super, super short. And usually when you have a problem that has something like that, where something really abrupt is happening, that's usually a clue that involves momentum. That's why I keep emphasizing that collisions, shocks, kicks, stuff like that are momentum problems, because that's usually when you use it. Okay, so the question I want to ask is, let's say, how much force acts on the car if the collision lasts around, let's say, 0.15 seconds. So super, super fast collision in the grand scheme of things. Okay, and let's go ahead and fill out some realistic numbers for some of these things. So let's say that before the collision goes, let's say that V naught was something like, okay, I think 10 meters per second is a realistic number. And we'll say that that's in the x hat direction. So I'm going to go ahead and define my coordinates as y hat is up, x hat is to the right, and that's a little right angle. Okay, so V naught goes to the right at 10 meters per second. That's just how fast the thing goes before it hits the wall. We know by convention that VF equals 0 because it collided. Hopefully it stopped. And then our problem statement where it says that the collision lasts for that long, that's going to be our clue that we have a delta t, and that delta t, I should use black for this. That delta t is equal to 0.15 seconds. Okay, and then the one other thing I need to know, because this is a momentum problem, is I need to know the mass of my car. And a typical car mass is something like 1,000, or maybe 1,500 is a better number. It's 1,500 kilograms. So I'm going to just annotate that here as m equals 1,500. Okay, so this is everything I know. I know how much mass my car has before it collides. I know how fast it's moving. I know that it stops when it collides. And then the problem statement gives me a clue that I'm going to use impulse because it tells me how long the collision lasts. So there's a statement within the problem that gives me my delta t. Okay, so if I want to find the average force, I'm just going to once again use this impulse equation that we defined up here. So F delta t equals the change in momentum. So I'm just going to go ahead and rewrite that. So F delta t equals P final minus P initial. And sometimes we call that J the impulse. But for now, we're not going to actually need to use that because we're asked to find the force. Okay, so here I'm going to go ahead and plug in what I know. So I know that the force is what I'm solving for, so I'm just going to leave it as F. Delta T I'm given, it's 0.15 seconds. And then for the momentum, we're going to need to make a quick simplification. So we know that momentum is defined as mv. So I'm going to write this as momentum is the mass of the car times v final minus the mass of the car times v initial. And those are both vectors. If I plug in the numbers I'm given, this equals 0 because or rather, this equals 0 because the car stops after the collision. So I'm going to go ahead and rewrite that as the force, which I don't know, times the amount of time the force acts, 0.15 seconds, equals, I pick up a negative sign, the mass of the car, which I think I said was 1,500 kilograms. So that's just me taking this down. And then I said that the velocity was equal to, I think I said 10 meters per second. So we'll put that as 10 meters per second. And then I had a little x hat there, keeping track of the direction of my velocity. So that's just me taking this and putting it down there. Okay, so I can go ahead and solve. Now all I'm going to do is I'm going to take this and divide it out over there to find this term. So if I write that out, I get that f is equal to negative. So I'm keeping that negative sign. 1,500 times 10 over 0.15. And let's go ahead and do the units real quick. So that's kilogram times meters per second. So I'm getting that from this and this. And then I divide through by seconds. So I should pick up another seconds. And then I still have this x hat, which I just bring straight down. Okay, so if I go ahead and I solve that out, when I did this at home, I got that this was minus 10 to the 6 was what this expression equals. Kilograms times meters per second squared, and it still is in the x hat direction. Okay, so what does this tell me? It tells me, one, that because the collision was super short, I get a super big force, right? So my mass was 1,500 kilograms, but my force in newtons is 1,000,000. And this kind of makes sense. This kind of makes sense because basically the shorter the collision lasts, the more you sort of concentrate that change in momentum into a really short amount of time. And so this quantity can increase really quickly if I have really abrupt events. That's why we like to use momentum for these problems. It really is about these really crazy high forces you experience during crashes and stuff. Okay, so that tells me that it's a big number. It also tells me that I do get the right units. Kilograms times meters per second squared is a newton. That's F equals ma units. It tells me that the force acting on the car is in the negative hat direction. That makes sense because the car is going that way, so that this brick wall is going to exert a force to stop it. So it's always in the opposite direction. So that's the negative sign there. And then it's a one-dimensional problem, so we stay in x hat. So this collision problem, by keeping track of all the vectors here, even though nothing crazy happened with the vectors, right, we're just working in one dimension, that allowed us to keep track of that negative sign and realize that stopping that car required a huge negative force from the brick wall in the car. Okay. So that's an example of, so this is an example here of external force during a collision. So now we're going to do an example of a collision with no external force. And the reason that we're going to emphasize this is because that implies net momentum is conserved. Okay, so here in this problem, I definitely didn't have conservation of momentum, right? I'm moving at m times v, then I stop, so my momentum got absorbed by the brick wall. Here we're gonna have a case where we don't have any external forces, and so we're gonna be able to use conservation of momentum to actually get us somewhere. Okay, conservation of momentum implies that the force equals 0 on average in some system. And that makes sense because if I say that J equals PF minus P naught, that's equal to F delta T. So if this is equal to 0, then I have the condition that PF minus P naught equals 0, which means that PF equals P naught. So that's why if you have no external force, momentum is conserved. And this is going to be useful in absence of force. Okay, so the example we're going to use is going to be two cars colliding at an intersection. We're going to treat the two cars jointly as defining one overall system that no external forces will act on. So I'm going to draw this from above. So we'll see how my drawing skills are. We'll do blue for the road. So I'm going to have car 1. It's kind of a long car. This is going to be some car that has a mass of 1,500 kilograms, same as the car that we just saw above. We're going to say it's heading into this intersection at 25 meters per second, so a little bit faster than we just saw. And then we're going to have another car that's going to head into this intersection. We'll make this a blockier car. That's going to head into this intersection at, let's say it's going a little bit slower at 20 meters per second. And let's say that this is a really big car, like a truck or something. So we're going to say that the mass of this car is 2,500 kilograms. So it's got a full 1,000 kilograms on the other car. Okay, so let's say that they've both. It's like the intersection on Duval Street where everyone just runs the stop signs. So they hit each other. And so as a result, they're going to collide at some time, and then we're going to get this sort of mess of a thing. So they've collided, and then that combined object is going to sort of recoil off at some velocity. So if you've seen this before in a different class, we would call this an inelastic collision, because they don't just bounce off of each other. They're going to crunch into each other, and then that object is going to sort of scatter out of the intersection off to the side of the road. So the question is, can we find V final of the wreck, where I'm going to call the wreck the two cars have sort of hit each other, and now they're going to sort of scatter out of the intersection because they came into it so fast. Okay, so I'm going to define my coordinate system. I'm just going to use y hat as up and x hat to the right, same as always. Draw my right angle. Okay, and I emphasize that for this problem, my system, for the purpose of momentum, is going to equal car 1 plus car 2. And I'm going to say that for this crash, when those two cars hit each other, car 1 can exert a force on car 2 for sure, right? That's what damages it. Car 2 can exert a force on car 1, but the sum of the forces across the entire system is 0. So there's no external forces. No one's coming in and pushing that car or anything. So when I think of the system overall as the two cars, there's no net force. There's just internal forces when the two cars hit each other. And this is going to come in handy because that means that I can write that P initial is equal to P final. And I'm spacing them out just because I'm going to write stuff under them. So if I say that there applies no external force, just the internal forces of the cars on each other, that means that P naught equals PF, which means I can start to add momenta. So I'm going to go ahead and do that. So initially the two cars, one of them is just moving in the x hat direction, and one of them is moving the y hat direction. So I'm going to go ahead and write down their momenta as a combined system. So that's going to write that car 1, I think I said, I'll just leave it as symbols and we'll substitute, had M1 V1. And I'll go ahead and write that as V1 x hat to start bookkeeping that vector. So it had some speed in the x hat direction. That's the car that came in to the right. And then we're doing the combined system as a single system. So we're going to add up the total momentum. So car 2 had a different mass. This is the heavier car. This is going at V2, and this is moving in the y hat direction. So we have one car moving to the right, one moving up, and we're going to write those two things together as the overall combined system. Okay, so that's before the crash happens. Then during the crash, right, a very short amount of time passes. And during that short amount of time, really high forces act on the cars mutually to each other. But external to the system, if I add up all the forces, they end up equaling 0 because car 1 hits car 2 as hard as car 2 hits car 1. Okay, so after the collision happens, sometime later, that wreck is sort of rolling out of the intersection. So I'm going to call that combined system the M1 plus M2. And I'm going to say that that has some velocity. I'm just going to leave that as a vector because my guess is going to be that it's not going to be along pure x hat or y hat. So I'm going to have to find that angle. Okay, so this is me just taking this expression, noting that I'm treating the entire two-car system as one thing. And then I'm going to bookkeep what the total momentum of that system is before. And then after, I've got the rect, which is these two cars smashed together, moving at some velocity that I don't yet know. Okay, so this is the vector form of a momentum conservation problem. But if I want, I can go ahead and write that in component form. So an equivalent way of writing down a vector addition problem is to split it into components. So let's go ahead and do that. And I'm going to start by writing the x component and the y component, because there's just the two components in this problem. Okay, so if I write that in component form, the initial momentum along the x direction is just m1 v1 x hat. The other car moves along the y hat direction, so I don't have to worry about it here. And that's going to equal m1 plus m2. And I'm going to go ahead and say the magnitude of the final vector. I'll put a little f there. And then I need to write cosine theta, where theta is going to be this angle. So if I have my rect that's drifting out of my intersection at some weird angle, Vx points that way, Vy points that way, those two components jointly can define that vector. Equivalently, that's like saying that I'm going to take this and project it onto that angle. Okay, so that's my x balance, and then my y balance is going to look shockingly similar, which is going to write m2 v2 y hat equals m1 plus m2 vf, and now I have to do sine theta y hat, where now I'm just, again, I have this vector that just describes the final position or the final velocity of the two cars, sort of amalgamation as it drifts out of the intersection, and I have to find the component along the vertical or y hat direction. Okay, so now I'm basically done with my problem, except for substituting in numbers and all that, because I know this, right? This was like 1500, that was 2500. These I'm given. These are going to cancel out because they appear on both sides. These are still the same. I'm just going to add them because the two cars smush together. This is an unknown. I have no idea what the final velocity magnitude is, and so is this. So I have two equations and two unknowns. So I have two equations, two unknowns. So that means that I now, if I wanted to, could do the algebra to solve for the magnitude of the final speed or the angle that the final velocity vector is directed along. So I'll go ahead and I'll do theta first because I think it's a little bit easier to do in class. But once you have one, you can get the other super fast. Okay, so maybe I say, what is theta of the rec? Where theta is just, how far, what direction do I drift out of the intersection at? So I can do this I can actually do this algebra quickly if I just, I can basically divide these equations by each other. So if I take this equation and I divide it by this equation, I should get m2 v2 y hat over m1 v1 x hat equals m1 plus m2 vf sine theta y hat. Then I should get m1 plus m2 vf cosine theta x hat. So now I'm going to cancel a whole bunch of things. So x hat appears on both sides here. That cancels. Y hat appears on both sides. So that's going to cancel. M1 plus M2 appears on both sides. So that cancels. And so does the magnitude, conveniently, of VF. So that cancels. So this actually is going to simplify a whole bunch to M2 V2, just the magnitude, M1 V1 equals the tangent of theta. So a bunch of stuff cancels out. And so in my problem statement, I believe I'm given that this is like 2,500. This is 1,500. This, I think, was 25 meters per second. And this was, I think, 20 meters per second. So I can go ahead and plug and chug, get a number there, do inverse tangent, and I'll get my angle. And then once I have my angle, I can then go ahead and plug it back into one of these, and I can find what V is if I want to know. And it should be some relatively small number because this pushed it that way, that pushes that way. So they add and they go in some new direction. Okay, so I'll just mention one thing because this is going to come up real quick. So momentum always conserved in collisions. but energy is not always conserved. Only in elastic collisions. So you'll see different cases of this. We'll talk about this a little bit more when we get to the energy conservation stuff. But just remember that you can always use momentum conservation for collision and recoil problems, but that doesn't mean you can necessarily use energy conservation. All right, thank you.